Sometimes in math, you see a formula with vectors, and it just looks abstract. But what if I told you that hidden inside of it is a secret that connects it to one of the most famous theorems of all time? It's a real puzzle, and the only way to crack it? We've got to draw a picture. Okay, so here it is. Take a good look at this equation. Doesn't that look kind of familiar? Like, if you just squint a little bit, it's almost the Pythagorean theorem, right? A squared plus b squared equals c squared. But, of course, it's not that simple. We've got vectors, we've got cross products, dot products, the whole shebang. And this was the exact question someone asked on Stack Exchange. What is this thing? Geometrically, what does it actually look like?
So that's what we're going to do. We're going to play detective here. First, we need to get to know our suspects, each little piece of this equation. Then, once we've got the clues, we'll put them all together and see if we can find that hidden triangle that I bet is at the center of all this.
All right, first up on our list, let's talk about the dot product. Now, the dot product is interesting. When you do A dot B, you don't get another vector. You just get a number, a plain old scalar. And this is what tripped up the original poster on Stack Exchange, right? How in the world do you draw a number? Well, the trick is understanding what that number means. Think of it like this. It's basically the length of vector A's shadow on vector B times the length of vector B. It's all about projection.
Okay, on to player number 2, and this one's a little different. Unlike that dot product, which just gives you a number, the cross product is way more visual right from the get-go. So the cross product actually gives you a whole new vector. But for our mystery equation, we only really care about its magnitude, its length, and this is where it gets really cool. The magnitude of A cross B isn't just a random number. It's literally the area of the parallelogram you'd make with vectors A and B. How neat is that? Okay, so let's do a quick recap. The dot product, it's a number, a scalar, all about projection and cosine. The cross product's magnitude, that's an area, and it's all about sine. These two completely different ideas, that's the key. That's the secret to solving this thing. All right, we know the players, we've got our clues, now it's time to put it all together. Let's build this thing, step by step, just like in that fantastic answer on Stack Exchange. And boom! This right here, this is the aha moment. Just look at this. You put the vector formulas next to the basic trig definitions for a right triangle, and the pattern is just, it's undeniable. The structure is exactly the same. That's our smoking gun. It tells us there has to be a right triangle hiding somewhere in our picture. So let's draw it out. We start with our two vectors, A and B. We can imagine them forming a parallelogram. But now, here's the critical move. You take the tip of vector A and you just drop a line straight down, perpendicular to vector B. And when we do that one simple thing, bam! A right triangle just pops into existence, just like that. This little triangle is the geometric heart of our entire proof. This is exactly what we were looking for. Okay, so now that we have our triangle, let's label the sides. The hypotenuse, well, that's easy. It's just the length of vector A. The adjacent side, the one next to our angle, that's our projection, A cos theta. And the opposite side, that's the height, which is A sine theta. And now we can bring in an old friend, the Pythagorean theorem. We just plug in what we know. Opposite squared plus adjacent squared equals hypotenuse squared. And when we substitute our vector parts in, we get this nice little equation right here. We are so close. Look at that equation. It's almost our mystery formula, but it's missing vector B. So what's the final piece of the puzzle? It's actually super simple. We just multiply the whole darn thing by the magnitude of B squared. We're just scaling everything up. And once we do that, everything just clicks into place. All of a sudden, you look at those terms and you go, hey, wait a minute. I know you. That first term is just the cross product's magnitude squared, and the second one is the dot product squared. And that, my friends, brings us to the grand finale. The puzzle is officially solved. There it is. We did it. We've shown with a simple picture that this super abstract vector identity is really just the Pythagorean theorem in a clever disguise. Every single part of it maps perfectly back to that little right triangle we drew, just scaled up by the length of vector B. But, okay, you might be thinking, that's a neat trick, but so what? Why does this elegant connection actually matter beyond just being a cool math puzzle?
Well, it matters because it's a beautiful example of how algebra and geometry are really two sides of the same coin. It takes a scary-looking formula and turns it into a picture you can actually understand. And this isn't just for fun. This identity, which is actually called Lagrange's identity, is a workhorse in physics and computer graphics. Calculating the torque on a spinning object or the way light bounces around in a video game, that's the stuff in action. It just goes to show you how something as simple as a right triangle can show up in the most advanced places.
And it really makes you think, doesn't it? How many other formulas that we just take for granted have these incredible, simple pictures hiding inside them, just waiting for someone to come along and draw them?